There's a mystery at the heart of reality that has haunted physicists, mathematicians, and philosophers for centuries. Why does mathematics work? Not just work in the sense of being useful for balancing checkbooks or calculating trajectories, but work with such unreasonable, almost supernatural effectiveness at describing the deepest truths about the universe. Michio Kaku has spent his entire career swimming in the mathematical depths of string theory and quantum mechanics, and he's arrived at a startling conclusion. Mathematics isn't just a human invention we use to describe nature. It's the language in which nature speaks. More than that, it might be the very substance of reality itself. And if mathematics is the fabric of existence, then the elegant, beautiful, seemingly intentional patterns woven throughout it suggest something profound. They suggest a mind behind the cosmos. This isn't mysticism or wishful thinking. It's a conclusion drawn from decades of working with equations that describe reality with impossible precision. When Kaku looks at the mathematical structure underlying quantum mechanics, relativity, and string theory, he sees something that looks less like random cosmic accident and more like composed music, a symphony written by a cosmic mathematician of extraordinary sophistication. The story begins with a simple but profound observation. The universe didn't have to be mathematical. Reality could have been chaotic, random, fundamentally incomprehensible to rational analysis. But it's not. Every single phenomenon we've ever studied, from the orbit of electrons to the expansion of galaxies, follows precise mathematical laws. Not approximate laws, not close enough laws, but laws expressible in equations that predict outcomes to stunning levels of accuracy. Take quantum electrodynamics, the theory describing how light and matter interact. This theory makes predictions accurate to 10 decimal places. That's like predicting the distance from New York to Los Angeles to within the width of a human hair. No other field of human knowledge achieves this level of precision, yet physics does it routinely, using nothing but mathematical equations. Kaku asks the obvious question: how is this possible? How can scribbles of symbols on paper, abstract mathematical objects existing only in minds and on chalkboards, predict with perfect accuracy what will happen in physical experiments? The physicist Eugene Wigner called this the unreasonable effectiveness of mathematics in the natural sciences. Unreasonable because there's no obvious reason why it should work this well. One possible answer is that mathematics is simply a tool humans invented to approximate reality, and we're just good at building useful tools. But this explanation fails on multiple levels. First, many mathematical structures were discovered or invented, depending on your philosophy, with no thought of physical application, sometimes centuries before physicists found uses for them. Complex numbers, involving the square root of -1, seemed like pure abstraction when first developed. Mathematicians played with them as intellectual curiosities. Then quantum mechanics came along, and complex numbers turned out to be absolutely essential. The Schrödinger equation, the fundamental equation of quantum mechanics, cannot be written without complex numbers. Reality itself appears to use these supposedly imaginary numbers. Non-Euclidean geometry was developed in the 19th century by mathematicians exploring what happens if you change Euclid's parallel postulate. It was considered interesting but physically meaningless, since obviously space is Euclidean, right? Then Einstein developed general relativity and showed that space-time is curved, following non-Euclidean geometry. The mathematicians had mapped the terrain decades before physicists knew that terrain existed. Group theory, developed as pure mathematics in the 19th century, became essential for classifying elementary particles in the 20th century. Riemannian geometry, created as abstract mathematics, became the language of general relativity. Topology, knot theory, abstract algebra, again and again, mathematical structures invented for their own sake turned out to describe physical reality with precision. This suggests something remarkable. The mathematical structures aren't inventions imposed on reality from outside. They're discoveries of patterns that already exist in reality. Mathematicians exploring abstract spaces are unknowingly exploring the structure of the physical universe. They're reading the source code of existence. Kaku takes this further. If mathematics describes reality so perfectly, Perhaps mathematics is reality. Perhaps the universe isn't made of matter or energy in any fundamental sense, but of mathematical relationships. Particles aren't little balls of stuff. They're excitations in quantum fields, and quantum fields are mathematical objects. Space-time isn't an empty stage on which events occur. It's a dynamic geometry, a mathematical structure that curves and flexes. String theory, which Kaku helped develop, pushes this mathematical interpretation to its logical conclusion. In string theory, the fundamental constituents of reality are one-dimensional strings vibrating in higher dimensional space. Different vibration patterns correspond to different particles. An electron is one vibration mode, a quark is another, a photon is yet another. But here's the key insight. These strings aren't made of anything, they're pure mathematical objects, defined entirely by their properties and relationships. If you ask what a string is made of, the only answer is mathematics itself. The universe, at its deepest level, is mathematical structure all the way down. This leads to what Kaku considers the most profound question in physics. Why these particular mathematical structures? Why these specific equations and not others? The laws of physics could have been different. The constants could have had other values. The symmetries could have been arranged differently. Yet, reality exhibits one particular mathematical structure out of infinite possibilities, and the structure that exists happens to be extraordinarily elegant. Einstein's field equations of general relativity possess a beauty that physicists describe in almost aesthetic terms. They're simple, symmetric, powerful. They explain the motion of planets, the bending of light, the expansion of the universe, black holes, gravitational waves, all from a single compact equation relating the curvature of space-time to the distribution of matter and energy. Maxwell's equations of electromagnetism show similar elegance. 4 equations describe all of electricity, magnetism, and light. They explain everything from how magnets work, to how radio waves propagate, to why the sky is blue, and they're beautiful in their symmetry and simplicity. The Dirac equation, describing relativistic quantum mechanics, predicted the existence of antimatter before anyone had observed it. Dirac was simply following the mathematics, and the mathematics told him there must be particles with the same mass as electrons, but opposite charge. When positrons were later discovered, they matched the predictions exactly. The equation knew something about reality before humans did. This happens repeatedly in physics. Mathematical beauty guides the way to truth. Equations that are elegant, symmetric, and simple turn out to be correct. Ugly, complicated equations turn out to be wrong or incomplete. It's as if the universe has an aesthetic sense, a preference for mathematical beauty. Kaku argues this can't be coincidence. Random processes don't generate beautiful mathematics. They generate functional but messy solutions. Yet nature consistently chooses the beautiful option. This suggests intentionality, a cosmic mind that thinks in mathematics and prefers elegance to chaos. Consider symmetry, a concept central to modern physics. Symmetries are mathematical transformations that leave something unchanged. Rotate a perfect circle, and it looks the same. That's rotational symmetry. The laws of physics show deep symmetries. They're the same everywhere in space. That's translational symmetry. They're the same at all times. That's time translation symmetry. They're the same regardless of orientation. That's rotational symmetry. These symmetries aren't just convenient mathematical properties. They have profound physical consequences. Emmy Noether proved that every symmetry corresponds to a conservation law. Time translation symmetry gives us conservation of energy. Translational symmetry gives us conservation of momentum. Rotational symmetry gives us conservation of angular momentum. The universe could have been chaotic, with different laws in different places and times, but it's not. It exhibits mathematical symmetries that ensure consistency and conservation. This looks like design, a cosmos constructed according to mathematical principles that ensure it will function coherently. String theory reveals even deeper symmetries. Supersymmetry suggests that every particle has a superpartner, a beautiful mathematical relationship that hasn't yet been confirmed experimentally, but that makes the mathematics work elegantly. T-duality shows that physics looks the same whether you're in a tiny, curled-up dimension or a large one. Once you account for how strings wrap around the dimensions, these aren't just abstract curiosities. They're hints that reality has a mathematical structure far richer than what we can directly observe. The visible universe might be just the surface of a much deeper mathematical reality, like how the visible spectrum is just a tiny slice of the full electromagnetic spectrum. Kaku points to the fundamental constants of nature as further evidence of mathematical design. The speed of light, Planck's constant, the gravitational constant, the fine structure constant. These numbers define how reality operates. Change any of them even slightly, and the universe becomes unrecognizable. Stars can't form, atoms become unstable, chemistry becomes impossible, life never emerges. The values these constants actually have fall within incredibly narrow ranges that permit complexity and consciousness. This is the fine-tuning problem. Out of all possible values these constants could have, they happen to fall in the tiny sliver that allows the universe to be interesting rather than boring, complex rather than simple, alive rather than dead. Some physicists argue this is explained by the multiverse. If countless universes exist with different constants, we obviously find ourselves in one fine-tuned for life because we couldn't exist in the others. It's an observational selection effect. But Kaku finds this explanation incomplete. It doesn't explain why the multiverse exists or why it generates universes with varying constants. It pushes the question back a level without truly answering it. The alternative is to recognize that the mathematical structure of our universe appears designed, optimized, for generating complexity and consciousness. The constants aren't random. They're chosen, though what or who does the choosing remains mysterious. Kaku suggests the answer might be mathematics itself, or more precisely, a mathematical intelligence underlying reality. This connects to Gödel's incompleteness theorems, which prove that any sufficiently complex mathematical system contains true statements that cannot be proven within that system. Mathematics contains irreducible mystery. No matter how much we discover, there will always be truths beyond our reach, accessible only through intuition or insight rather than formal proof. Kaku sees this as evidence that mathematics is more than human construction. If we invented mathematics, we could in principle know everything about it. But Gödel showed we can't. Mathematics has properties independent of human minds, properties we can discover, but not fully control or comprehend. This suggests mathematics exists in some Platonic realm, independent of physical reality, yet somehow connected to it. The physicist Max Tegmark takes this idea to its extreme with his mathematical universe hypothesis. Tegmark argues that physical reality is mathematics, not described by mathematics but actually is mathematics. Every mathematical structure that can exist does exist as a physical universe somewhere in the multiverse. Our universe is one particular mathematical structure among infinite possibilities. Kaku doesn't go quite that far, but he acknowledges the possibility. What he emphasizes is that whether mathematics is reality or describes reality, its effectiveness in physics is so extraordinary that it demands explanation. And the most satisfying explanation is that a mathematical intelligence structures the cosmos. Think about consciousness and mathematics. Human minds can understand the mathematical laws governing reality. We're part of the universe, made of the same particles following the same laws as everything else. Yet we can comprehend those laws, can write them down, can use them to predict and manipulate nature. The universe has become conscious of itself, capable of understanding its own mathematical structure. This seems like more than coincidence. If the universe were truly random and purposeless, why would it generate beings capable of understanding it? Why would the mathematics in human minds match the mathematics in external reality? The fact that our neurons, firing according to electrochemical laws, can grasp quantum mechanics and relativity suggests a deep connection between mind and cosmos. Kaku often quotes Einstein, who said that the most incomprehensible thing about the universe is that it's comprehensible. We can understand it. Not completely, not perfectly, but enough to unlock atomic energy, land on the moon, peer back to seconds after the Big Bang, and predict the existence of black holes and gravitational waves. A random, mindless universe has no obligation to be comprehensible to the conscious beings it accidentally produces. Yet it is comprehensible through mathematics. And mathematics itself shows signs of intelligence. Consider the Mandelbrot set, generated by a simple equation, yet producing infinite complexity. Zoom into the boundary, and you find galaxies of intricate patterns, self-similar structures repeating at every scale. Simple mathematical rules generate inexhaustible richness. The universe works the same way. Simple laws, the Schrödinger equation, Einstein's field equations, produce all the complexity we observe. Every galaxy, every star, every molecule, every thought in every brain, all emerge from a handful of fundamental equations. This is what physicists mean by elegance. Maximum explanatory power from minimum initial complexity. Random processes don't work this way. They generate complicated rules that explain limited domains. Only intelligent design, whether by human engineers or cosmic architects, produces simple rules that generate complex outcomes. The fact that physics keeps finding simpler, more elegant formulations of natural laws suggests we're discovering the thoughts of a mathematical mind. String theory exemplifies this search for ultimate simplicity. The goal is to reduce all of physics to a single equation, a theory of everything that explains why the universe is the way it is. String theory attempts this by proposing that one-dimensional vibrating strings in 11-dimensional space generate all particles and forces. It's extraordinarily ambitious, and the mathematics is so complex that even the smartest physicists struggle with it. But the vision is simple. One fundamental object, the string, governed by one fundamental principle, minimizing its action, produces everything. If string theory is correct, then the entire universe, in all its bewildering complexity, is actually an expression of deep mathematical simplicity. Every atom, every force, every dimension, all vibrations of strings following one master equation. Kaku sees this as glimpsing the mind of God. Not God in any traditional religious sense, not a bearded man on a throne judging human behavior, but God as the mathematical intelligence that structures reality, the cosmic consciousness that thinks the universe into existence through equations of perfect beauty and power. This God doesn't interfere with nature because this God is nature, or rather is the mathematical laws that nature follows. Miracles don't happen because there's no need for them. The laws themselves are miraculous enough. That reality follows consistent, comprehensible, elegant mathematical principles rather than being formless chaos is the deepest miracle of all. Prayer doesn't work in the sense of asking for divine intervention, because the divine doesn't intervene. It simply is, eternally expressing itself through mathematical necessity. But contemplating the mathematical structure of reality, what physicists do when they work on equations, becomes a form of communion with this cosmic intelligence. Understanding physics is understanding the thoughts of God. This perspective resolves the apparent conflict between science and religion. They're not opposing ways of knowing. They're complementary approaches to the same underlying mystery. Religion attempts to relate to the intelligence behind existence. Science attempts to decipher the language that intelligence speaks. That language is mathematics. The mystics and contemplatives throughout history who spoke of divine order, cosmic harmony, and the universe as a great thought were intuiting what physics now demonstrates rigorously. They lacked the mathematical tools to make their insights precise, but they sensed the truth. Reality is fundamentally mental or informational rather than material. Consciousness and mathematics are more basic than particles and forces. Kaku acknowledges this sounds like idealism, the philosophical position that mind is more fundamental than matter. And in a sense it is. But it's not solipsism. The mathematical structures aren't private mental constructions. They're objective, existing independent of any individual mind, yet still essentially mental or informational in nature. Think of it this way. A computer program is information. It's not material in any fundamental sense. You can write it on paper, store it on hard drives, transmit it over networks, run it on different hardware. The program itself is abstract, mathematical, mental. Yet when running, it produces concrete outputs. It causes real effects. The universe might work similarly. The mathematical laws are like the program, abstract and eternal. The physical world we experience is like the output, the execution of those laws producing space, time, matter, and energy. We're characters in the cosmic computation, patterns in the universal program, conscious subroutines able to examine our own source code. This perspective makes certain paradoxes of quantum mechanics less mysterious. Quantum mechanics treats reality as probabilities until observed, then collapsing into definite states. This has bothered physicists for a century. How can reality be indefinite? What counts as observation? Why does measurement matter? But if reality is fundamentally information, then it makes sense that unmeasured systems exist as multiple possibilities. Information can be in superposition. It becomes definite only when accessed, when one possibility is selected and the others discarded. The quantum wave function is just the mathematical description of all possible states. Observation is the universe deciding which state to actualize, executing one branch of the cosmic program. Entanglement, where particles remain connected regardless of distance, also becomes less mysterious. If reality is mathematical relationships rather than physical objects, then particles that interact become mathematically related. That relationship persists even when they're separated. It's not that information travels faster than light between them. It's that they're parts of one mathematical object, one equation, and knowing one part tells you about the other because they're linked by mathematical necessity. The holographic principle, which suggests that all information in a volume of space can be encoded on its boundary, supports this informational view. It implies that three-dimensional reality is in some sense a projection from two-dimensional information, like a hologram. Space itself might be an illusion, a convenient way of organizing mathematical relationships rather than a fundamental feature of reality. Kaku sees all these strange features of modern physics as pointing toward the same conclusion. We've been thinking about reality backwards. We assume matter is fundamental and consciousness is an emergent accident. But the evidence increasingly suggests the opposite. Consciousness, or at least mathematical intelligence, is fundamental. Matter is the emergent phenomenon, what mathematical patterns look like from the inside. This has profound implications for understanding ourselves. We're not separate from the cosmos, observers standing outside looking in. We're the cosmos observing itself. Mathematical structures examining their own nature, the universe's way of knowing what it is. Every thought you have, every equation a physicist solves, every moment of awe at natural beauty, these are the cosmic consciousness experiencing itself through countless perspectives. The ancient Hindu concept of Brahman captures this. Brahman is the ultimate reality, the ground of all being, pure consciousness that manifests as the multiplicity of existence while remaining fundamentally one. Atman, the individual soul, is ultimately identical to Brahman. The separation is illusion. Kaku's physics translates this ancient wisdom into modern language. The mathematical intelligence underlying reality and the consciousness experiencing it are not separate. They're two aspects of the same thing. This doesn't make us God in any egotistical sense. We're tiny, limited expressions of cosmic consciousness, like individual waves in an infinite ocean. But we're not separate from that ocean. We're made of it. The mathematics governing our neurons is continuous with the mathematics governing stars. The consciousness reading these words right now is a localized instance of the consciousness that permeates reality. If this seems too mystical, consider what physics actually tells us. Your body is 99.9999% empty space. The solid matter is mostly void, with tiny quantum clouds we call particles suspended in it. Those particles aren't really particles. They're excitations in quantum fields, probability waves that collapse to definite positions only when measured. The quantum fields themselves are mathematical structures, existing in higher dimensional spaces, most of which are curled up too small to see. So, what are you really? You're a pattern, a temporary organization of quantum fields following mathematical laws, generating the subjective experience we call consciousness. You're not separate from the universe. You're a way the universe organizes itself, one configuration among countless possibilities, but all arising from the same mathematical foundation. Kaku's vision is both humbling and exalting. Humbling because it puts human concerns in cosmic perspective. The mathematical structures underlying reality don't care about human drama, politics, or individual desires. They simply are, eternally expressing themselves. But exalting because it means we're participants in something unimaginably vast and profound. We're not cosmic accidents. We're the universe understanding itself, mathematics becoming conscious of its own nature. The search for a theory of everything, the holy grail of physics that Kaku has dedicated his life to, is really a search for the master equation. If found, this equation would contain, implicitly, everything. Every particle, every force, every galaxy, every thought. It would be the universe's source code, the algorithm that generates all of reality. Kaku believes this equation, if discovered, will be shockingly simple. Perhaps one line, perhaps even shorter, maybe a single symbol representing a profound mathematical truth. And in that equation, he expects to see the signature of intelligence, elegance so perfect it could only be intentional, beauty so profound it reveals the aesthetic sense of the cosmic mathematician. Some might find this vision cold or impersonal. Where's the loving God who cares about individuals? Where's divine intervention, answered prayers, or personal salvation? Kaku's God doesn't provide these comforts. This God doesn't grant wishes or override natural law. This God is natural law, immanent in every equation and constant. But there's profound meaning in this vision too. It means everything is sacred because everything is mathematics, and mathematics is divine. The spiral of a nautilus shell, the orbit of planets, the frequency of light from distant galaxies, all are expressions of the cosmic mind. Scientific inquiry becomes spiritual practice. Understanding nature becomes knowing God. The distinction between sacred and secular collapses because everything is, at its deepest level, the thought of infinite intelligence. Whether Kaku is right that mathematics reveals the mind of God depends partly on definitions. If God means the mathematical structure of reality, the elegant laws that govern existence, the intelligence embedded in the fabric of the cosmos, then yes, mathematics does reveal this. If God means something else, a personal being who intervenes in human affairs, then that's a different question beyond physics' domain. But what physics unambiguously shows is that reality is mathematical to its core, that this mathematics exhibits extraordinary elegance and apparent design, and that conscious beings like us can comprehend it. These facts demand explanation. Kaku's explanation, that mathematical intelligence underlies existence, that the cosmos is essentially mind thinking itself into being, is at least as plausible as any alternative. And it's an explanation that satisfies both the head and the heart. The head, because it's grounded in rigorous physics and mathematics. The heart, because it suggests that existence is ultimately meaningful, that we're participants in a cosmic intelligence, that understanding the universe through physics is a form of enlightenment, glimpsing the infinite through the finite. The mathematical beauty that physicists chase, the elegant equations they seek, these aren't just human aesthetic preferences. They're signposts pointing toward the nature of reality itself. And reality, when examined closely through the lens of mathematics, looks less like a purposeless machine and more like a mind, a consciousness, a God who speaks in the language of symmetry, elegance, and mathematical truth. That's what Michio Kaku sees when he looks deep into the equations. And that's why he believes mathematics reveals the mind of God behind the cosmos.